Hello, and thank you for watching. Looking forward to explaining potential energy and how it is related to kinetic energy and even the conservation of mechanical energy in this set of lecture slides. So let's jump right in. Okay? So, first things first, let's define what we mean by gravitational potential energy. We know that energy is required to lift an object against its own weight. We know that work, at least in the same direction, with force and displacement being in the same direction, done against gravity to lift a mass m, height h, is going to be W equals mgh, because that's going to be force is weight, mg, and then displacement is just the height h. Now, if we were to drop an object from that same height, it would have that it would have that kinetic energy, mgh, when it hits the ground. So remember, potential energy is not so much potentially energy as much as it is potentially work. It's potentially energy that could be released, and thus it is stored energy. So the stored energy is the gravitational potential energy, and that's going to be the gravitational potential energy at height h is going to be given by this very important equation. Capital U subscript g is mgh. This is the important equation for gravitational potential energy. Notice that height h is defined here above the ground. I'll say more about that as we go along. And notice that potential energy here is representing the stored energy that could be released as the object falls. Okay. Suppose we lift a book slowly from height 0 to yb. So height 0 to yb. Now, instead of thinking about height, let's instead think about a y-axis. So the work done on the book is mgyb. Since there's positive work done on the book by, let's say, a hand lifting up the book, the energy of the book increases, but the kinetic energy did not increase, so where did the energy go? Since the kinetic energy would be the work done by gravity, if the change in kinetic energy is the work done by gravity, the kinetic energy would be mgy. So notice that the potential energy would become kinetic energy. Now, one thing I want to discuss with respect to potential energy is that it is path independent. Let's explain what we mean by this. This is a very important concept. That any potential energy, not just gravitational potential energy, that's the way I'll be explaining it here, but any potential energy is independent of the path, in other words, how the mass was raised, and it's independent of the trajectory. It only depends upon the initial and final positions. Here, all that matters is the height h in the equation of gravitational potential energy. So notice that if this is our equation, in this example diagram, person A is lifting a television up from point A to point B. But they're lifting it straight up with a rope in tension. Whereas another person is walking the same television up the stairs, and they're still going from point A to point B, but they're getting there by a much longer path. Either way, the TV mass was lifted upward. The same amount of work to raise the television to new height h was achieved. So notice that given that the potential energy equation says nothing about the path it took to get there, both have the same potential energy. If we define h equals 0 as the ground, that's where no gravitational potential energy is found, then each of these televisions would have the same gravitational potential energy. Now let me make an important note. When it comes to potential energy, if no one tells you where the 0 point is, you are free to choose the h equals 0 point. I would recommend choosing the h equals 0 point at a point that's convenient. So typically the ground level is set as height 0, but you might want to set height equal to 0 to somewhere else. Maybe that's like the lowest height value of your object, and you could imagine that perhaps, if you've seen an earlier video that I've posted, a pendulum is, let's say, swinging, and the center of the mass of the bob of the pendulum we set to be height equals 0. The pendulum is off the ground, but if we set that to be height equals 0, that's 0 potential energy. Okay, so I want to mention this notion of conservative force. Any force which can be described by a potential energy is a conservative force. So thus we find that gravity is a conservative force. The work done by the gravity force only depends upon the initial and final height. And this is in the absence of dissipating forces, because dissipating forces are not conservative forces. But since gravity is a conservative force, we can define the gravitational potential energy from it. In both of these examples, the work done by gravity only depends upon the change in height. Now, these conservative forces will conserve energy, and we have to define what that energy is. So let us define this notion of mechanical energy. And the total mechanical energy, often abbreviated capital ME or capital E subscript mech, mechanical energy, is going to be the sum of the kinetic energy plus the potential energy. In this case, we're focusing directly on gravitational potential energy, so that's the equation that we'll have. Now, by contrast, a non-conservative force is one that adds or subtracts mechanical energy from the system. For instance, friction on an object or a person pushing an object will be a non-conservative force that will add or take away mechanical energy to the system. Notice work done by a non-conservative force depends on the path taken. Notice that if we have a car here and we want the car to achieve a height of 18 centimeters, let's imagine this is a toy car, that toy car can either take the short purple path or it can take the longer alternate path with the loop-de-loop. But notice that without friction, the final velocity that the car would achieve would only depend upon its initial height 0 and its final height 18 centimeters. So that would be in the absence of friction. But if there is friction, the final velocity for this car, at least the magnitude of it, the speed, would be slower if the car takes this alternate path, because the path length is quite substantially longer. There's a longer path for friction to rub against, and more energy should be dissipated. That is, more energy should be transferred into heat, which is not mechanical energy. Okay, so in any interaction, I want to emphasize, the total energy is constant. Energy is one of the most fundamental quantities in the universe. It can neither be created nor destroyed, only changed from one form to another, namely transferred around. Now for motion, typically we define it this way, that the initial mechanical energy should be the final mechanical energy if all the forces are conservative. But if there are non-conservative forces, then they will do non-conservative work, and non-conservative work will either add or take away mechanical energy. Remember, mechanical energy is the sum of kinetic plus potential, and initial and final are the subscripts that go along with here. By the way, energy is being provided or taken away, in this case, in this class, usually by work being the transfer of energy. Now, in general, in later physics, energy can be added or taken away by things like heat, chemical energy, electrical energy, even radiation, all kinds of things. And that would be included in your conservation of energy equations, but that would be considered in later physics. For the sake of this course, we focus on energy transfer due to work. Okay, so this conservation of energy example tells us that if the mechanical energy initial equals the mechanical energy final, when there's only conservative forces, Newtonian motion problems become much easier. We don't need to know the angle of slope of this roller coaster all the way through. All we need to know is the starting height, the ending height, and the initial velocity to solve for the final velocity. I will show that in a later video. Okay, and then finally, here is a 4-frame movie of a particle in free fall. Notice that this particle that's in free fall is going to conserve its mechanical energy. Notice that when we launch the ball, its velocity is largest, it's all kinetic energy, but its height is 0. Now, as the object ascends, its height increases, so its potential energy increases, its kinetic energy decreases, and now the potential energy is all the kinetic energy that was originally taken away by the increase of height. That is to say, gravity did negative work on the ball because the displacement was upward, but the gravity force was downward. But when gravity was doing negative work, we were actually storing up gravitational potential energy. When the ball reaches its final height, let's call it yc, the potential energy is equal to the total energy. Notice the kinetic energy is 0, and we've reached the turning point. So if you're plotting an energy versus position graph, the turning point is just where the kinetic energy is equal to 0, or you could say the potential energy equals the total energy and the object should change direction. So after it leaves that turning point, it starts to go downward. And notice yd, if that's equal in height to yb, then the speed should be the same as it was in situation B, but the velocity direction should be downward. And again, the object has kinetic energy again. It has gravitational potential energy, which is smaller than it was at the maximum height, the turning point. But it's going to lose potential energy and gain kinetic energy. This notion of transfer of energy and the conservation of mechanical energy is so fundamental to physics. So I want to thank you for your attention. I want to thank you for listening. And please have a look out for later videos where I perform example problems.